Hi everyone, my name is Riccardo De Luzio, and today I'll be presenting Learning Graph Regularization for Guided Super-Resolution. This is joint work with Alex, Stefano, Stefania, Jan, and Konrad. Super-resolution is the task of increasing the resolution of a given source image, which can be, for example, a depth map. In the specific case of guided super-resolution, we're also given an additional guide image, which comes at the desired resolution, but from a different modality. For example, a high-resolution RGB image. Most current solutions are variants of a two-branch deep neural network. These perform well if the training set is large and if the test images are close to the distribution observed at training time. However, when these conditions are not met, they underperform. In particular, the predictions are not guaranteed to be consistent with the source image when downsampled back to the original resolution. We propose to address this issue by combining the power of deep feature extractors with the rigor of graph-based optimization in an end-to-end trainable framework. We train a deep feature extractor to derive the edge potentials of a four-neighbor affinity graph defined on the image pixels. This graph is then used as a regularization in a per-image optimization layer to reconstruct the target image. Learning the graph is extremely important. In this example, we see that a graph built on color features alone, such as in the top right subfigure, results in the text being carried over to the high-resolution prediction. Whereas the graph based on the learned features presents large affinities around the high contrast text in the middle of the object, which effectively results in a smooth depth prediction. This is only possible because the learned edge potentials encode rich context information over large receptive fields. Let's now deep dive in our optimization layer. The prediction that our model makes is the solution to this quadratic problem, which has a data fidelity term that effectively forces the prediction to be consistent with the source when downsampled to the original resolution. And a second term, the graph regularizer, which measures how smooth our signal, or in this case, our prediction is on the learned graph represented by its Laplacian. This quadratic problem is equivalent to solving a sparse linear system, which we can efficiently do with the conjugate gradient method. To enable our feature extractor to be best suited to the task at hand, we obviously also need to backpropagate through the optimization layer. To do so, we need to compute the gradient of the loss function with respect to the prediction and map it to the individual entries of the graph Laplacian L. We take inspiration from the fast bilateral solver by Baron and Poole and apply the implicit function theorem, which gives us these two equations. And as we can see, the backpropagation now results in solving a second linear system, for which we also employ the conjugate gradient method. Note that the derivative with respect to the Laplacian is a dense matrix, which is impractical, as for a 256 by 256 pixel image, that results in approximately 4 billion elements. Fortunately, we can exploit the fixed graph topology and only compute the non-zero elements, which correspond to the index pairs of the four neighborhood. Finally, we evaluated our method extensively on the RGB-guided depth map super-resolution task, and we consistently outperform existing methods both quantitatively and visually, as can be seen in this example depth maps from the Middlebury dataset. Please refer to our paper for more details about our method and additional results. You can also find our implementation by scanning the QR code. And with this, I thank you for your attention.